And for the numerical model, it's important that the regional aquifer flows only causes, mostly causes horizontal flow in the basalt aquifer, and it has insignificant displacement and salinity difference in the deep marginal wells. So we can still use those to calibrate the 3D models. And I think that's ending the borehole flow. I'm going to come to the sea level rise, unless you have any questions for this. Yes?
So here you discuss model calibration. So when you calibrate your model, here you're talking about the salinity profile. So you really try to calibrate the dispersion coefficients, hydraulic conductivity. Which one you put your effort on? The salinity profile is more depends on the numerical number of dispersion coefficients,
yes,
rather than hydraulic gradients or hydraulic conductivity. What kind of value roughly you use for dispersion?
It's too long ago. I really have to look up. I don't know at the top of my head, but yeah, we try and not match. But you see how different these profiles are already by trying to match. You try to match all of them, you know. So therefore, with the 2D model, you always run into some problem. The main thing you see that here, we're modeling. We're kind of getting the shape of the observed profiles, but our transition zone is a little bit too thin. So you would have to have a deeper. But the curve overall in the inlet areas kind of matches good. So I think we try to still use try to calibrate the dispersion towards those. But yeah, as you see, there's a lot of heterogeneity along the shoreline between east and west, and also from every single case, how much borehole flow you have, and these steps disturbed. Of course, doesn't make it easy to calibrate it too. But I would have to look which number I used. I don't know off the top of my head.
You raised a very interesting point to explain the shock as well as the gradual change salinity profile by introducing the idea of a borehole flow to explain why it sometimes become a shock step type.
Yeah.
On the other hand, another way to explain is the step type, the shock profile indicates a very small dispersion coefficient. The other one indicates a large dispersion coefficient. So there are two ways to look at from hydraulics or purely from a mixing nature.
You're right. You do in the whole area from, let's look at the orange profile, from this point up to here, there's not much mixing with the aquifer. So basically you would have to have two things. You have to have a gradient that moves the water up, and you also have to have limited inflow from the area, because otherwise all these areas would provide, if there's upward flow, it would suck it out of every depth you would come in. And then you would have mixing, and you would have not this sharp step. But it appears that the salinity pretty much remains constant from this depth on up to that depth. So there's no interaction between, over this entire length, there's no interaction between the water in the well and the aquifer. So otherwise it would disperse, it would start to mix.
Sorry.
Tom?
Very Kolja, you used also conductivity to calibrate for the hydraulic head.
Yes. Yes. That's why we also match the water levels. Yeah. Thomas?
Just to follow up on that, from an oceanographer's perspective, when I see a CTD profile like that, we would interpret it as a result of an instability, resulting in strong mixing, and then you have a homogenized water column. So I was curious if in your data, if you see a relationship between the function, the step size and the distance from the shore, because distance from shore would seem to have a changing stratification and changing tidal forcing, and those two might influence the stability of your stratified water in the borehole.
I didn't plot that. I only looked at length of that step and distance to pumping centers. And even that one didn't give a clear correlation that you can say, oh, the closer you're pumping, the higher the larger the step is. So you do see those steps, but I wouldn't say that the length of the step is really determined by the distance to the pumping center. It's more the severity of what happens is the more you pump, the more outward it goes, because you're sucking more, which is obvious because you're sucking more salt water, or you're sucking harder through that hole, getting more brackish water up, which remains the same within the hole. I haven't looked at the distance to shoreline. Out of the top of my head, I would say no, but I haven't looked at it. Okay, move on to the sea level rise. All right, so here we go. A little switching gears. How time is it, just to see? What?
It's 3:42.
42. 18 minutes. I can do that. All right, no questions. Okay, this is a recent study I did together with Chip Fletcher. And the way the whole thing came up, that he always asked me, so, because I know, I mean, he's doing the inundation and coastal flooding due to sea level rise for a long time already. And so he asked me, so Kolja, what happens when sea level rises? You know? And I always thought, like, what happens to the freshwater aquifer? So like, well, not much. I mean, it just moves up a little bit, but, you know, it's no big deal. You know, the freshwater lens is so thick, as I showed you the picture before, 1,000 feet, almost 1,000 feet below sea level at the thickest point. That midpoint, if that one moves up a little bit, who cares, you know? I wasn't really thrilled by the whole thing. And he's like, no, I mean flooding. I mean, what happens in the coastal area? So then I understood that he's asking from the perspective of what happens to the water in the caprock. No hydrologist in Hawaii looks at caprock water. That's brackish water. Nobody cares. It's not a water resource. You know, there's no monitoring. There's just no interest. It's just useless water. And so I was like, first of all, I had to think a little bit. It's like, well, the caprock water is a little different, of course, than the basalt water. It's an unconfined aquifer. It's in the sediments. And yeah, but it's a typical freshwater-lens. And so he asked me, so what happens? He's like, well, I mean, it just rises with the sea level. It's like, oh, really? So how high is it above ground? It's like, well, it's certainly above mean sea level. He's like, oh, we're going to look at this. And then he started the whole thing. And together with some good digital elevation maps, we were able to come up with a very good study. So I'm making this really short because if anybody's interested in climate change and the causes and all the effects, you have to go to the talk of Chip Fletcher. And actually, I borrowed a few of his slides for this interesting debate. And but just for completeness, I'm going to include them here. So what happens? Sea level or climate change causes air and sea temperatures to rise. Ice sheets and glaciers melt. And due to the thermal expansion of ocean water, we do see a sea level rise. Very short, but there's certainly a lot more to it, but you can melt it down to this. What that causes is mostly erosion and coastal flooding. Now, what has been overlooked so far, and what people are not realizing, that the coastal groundwater levels are above mean sea level, which means they're higher than sea level. So every other assessment before would just look at rising the ocean water level of the sea level at a certain amount, and then see which areas are inundated or flooded. And now, with the fact that the coastal groundwater levels are above mean sea level, and they rise simultaneous with sea level because it's the freshwater lens that floats on salt water. You see tides inland, everything but moves in the ocean, moves in the aquifer. They rise with it, especially if it happens over 100 years. There's no doubt that they're going to just rise with it.
But I thought the caprock was impermeable. How is it?
It's not impermeable. It's just less permeable. And it's a lot less permeable than the basalt aquifer, which is very permeable. And that means it just provides a barrier to the outflow of fresh water to the ocean and also inflow of salt water. Now, I think one thing with the caprock, and I maybe can show you that later in a more detailed slide, is that it consists of a lot of different things. Coral, debris, there's even limestone caverns. There's huge parts which have a very large conduits of easy flow through it. But overall, compared to the basalt aquifer, the permeability is lower. And I think one of the most important things is that the contact between caprock and basalt, there's a fairly thick zone of weathered basalt. And the weathered basalt, it really has a low permeability. And that provides one of the biggest barriers to flow. So even if you do have rather good flow through the caprock, the interaction between basalt and the caprock is low. And that's why you get this barrier. So if we do now include the groundwater levels into our analysis, we find out there's a lot more flooding going on. So real quick, global temperature rise over the past 40 years is going up. Ice sheets are melting. I'm not going to go too much into detail. Sea levels are rising. You've all seen this many times. Global sea level currently rises at about 1 foot in 100 years. There's certainly areas where it rises more than others. There's even areas where it's going down. Alaska seems to be rather going down. Other areas like Texas are hard hit. Oahu, Hawaiian Islands seem to be kind of in the middle of it. If you look at the Honolulu tide gauge right now, you do see a current rate of rise from 1900 to the last 100 years. It's about ½ a foot. So not really that much, especially if you compare it with the projections. But, well, this is something I didn't assess, how much sea level will rise in the next 100 years. I'm just taking numbers that are spit out by other people and applying that. And of course, you can apply any number you want to and just see what happens. So let's go with what the general scientists have agreed on, that by the middle of the century, sea level is going to rise 1 foot globally and 3 feet by the end of the century. Now, of course, that could be all different 5 years from now with new models, and it also could be locally different. But let's just use that as a starting point so we can run our little model. One of the effects that sea level rise has is that erosion is going to increase. In fact, 70% of all the Hawaiian beaches are eroding. And if anybody been through the news, you've probably seen these pictures from the North Shore, which are more attributed to higher water levels, which is the same thing, right? So you have high water levels, all of a sudden, beaches are exposed to wave action that they haven't really been, or areas of the beach are exposed, or sand gets carried away, and all of a sudden your pool in the front yard is a little bit larger than you had it. Also what happens is flooding, and that is now, but this is nothing new. So obviously sea level rises and areas get flooded. But here comes a new thing. So this is again our theoretical cross-section through an aquifer on Oahu. Made the caprock a little thicker here because we have more interest in the area of the caprock, but you do see a freshwater-lens. And right now, the freshwater-lens is not really entirely true for the basalt aquifer because I don't really care too much about the basalt aquifer now. So don't really nail me on the interface between this, what the aquifer exactly does. The model that I showed you earlier shows a better picture of what really happens. Anyway, the main thing is the water table slopes upward, and at this point everything is in the ground, nobody knows about it, nobody sees it, everything is fine. But now you start rising your sea level. And with the sea level rise, you're not only getting the areas here inundated, or anything that might breach through, you're also coming from underneath. So everything that's below your new, well, not only below the new sea level, but also below your projected groundwater table, which is now above ground, will be inundated. So you do have a lot larger areas, and so we distinguish between the areas that are inundated from the ocean side as marine inundation, and we term the other one groundwater inundation. The interesting part is nobody has looked at this. Nobody has really thought this through. I mean, borehole flow, I can't say I invented that because there's a lot of people 20 years ago that already looked at that and said, well, we do see these steps, it's probably borehole flow. But nobody looked into the details. But this one, nobody has really looked into it. Nobody cared about it.
Given that this is a very slow process and going to take 100 years,
yeah,
certainly there would be alterations in the surface water flow regime to drain this.
The drainage would certainly, yeah.
Oh, it's flooding. What will we do?
Right, but the biggest thing is you can't really escape it. If the groundwater table rises with it, there's no way to escape it. The only way you can do is pumping, and that's what they do in Venice. They're pumping. That's what they do in New York.
Or channelize it.
Channelizing, yeah, draining. I mean, that's what they do in Holland, right? Everything is drained, so it just like it goes out. So I have to still stress that there's, due to this effect, there's no significant impact on the water resources in the Rotzoll aquifer, because I showed you before, your midpoints at say 1,000 feet or 900 feet below sea level. That one rises also 3 feet. Doesn't matter. And the first thing you see is the storm sewer inundation, so water would come out through the sewers onto the streets at high tide. And later on, you would also see groundwater coming up. Now this is not a good picture because, well, this is the groundwater table. So this is the hole right in front of our office. It's about 3 feet below the ground surface, measured at high tide. Oh, measured at low, measured at when the mean sea level was 0. So you add 3 feet to it when you sea level rise at high tide, you're on the street. Water comes out of this. So, and unless we find a way to drain it, to pump it, or to get rid of the water, because you can't make a barrier, you cannot just, you cannot seal yourself from that. So let's look into the mathematical model I applied first. I included tidal influence, so I estimated at which rate the tides disappear, the distance from the shoreline, and I also looked at observed water levels in the caprock aquifer, which I didn't really find many, but a few. And so I tried to calibrate the analytical solution of Glor to that, wet years and dry years, took an average between those as my black line, included the tidal influence at high tide, so at mean high water is about a foot above mean sea level. And then you're going in, and the further you go inland, the less tidal influence you have, and at some point here, it's so small that it's not even recognizable anymore. And now we can take that black line and apply it in a very crude way in our 3D study area, which of course is not perfect, but this is the first step of approximating our prediction. So this is my predicted, or my estimated groundwater table at high tide in feet above mean sea level. It goes from about a foot at the coastline to about 3 feet inland, and clearly in the reality it's going to be different because you have different geology at different parts, and it would be draining different in other areas, but this is just an approximation of what our sloping water table inland would be. Now if you add that to your flooding scenarios, let's see what happens. So first, we're looking at what Geophysics always calls the bathtub modeling. So we're just raising the sea level by a factor, say 1, 2, or 3 feet, and then look at our digital elevation map and see which areas are underwater. And of course, you only count the ones that are directly connected to the ocean, because the other ones, although they might be below sea level, can't be reached because the water is not expected to flow there. Now, well, in the long term, it might even go through the ground, but that would be already groundwater inundation, wouldn't it be? Anyway, let's turn on groundwater inundation now and see what happens if we include the groundwater table. That's a lot more. That's a lot more. And in fact, it's for all the 3 scenarios, 1, 2, or 3 feet, the inundated areas is more than 50% is due to groundwater. So it doubles pretty much the prediction from sea level rise, what we have. Now you can argue how much feet of sea level rise we're going to see, and because certainly you can improve the model with better estimates of measured groundwater table, but the process is still the same. The process will be still there. And now the consequences are obvious. What happens in this area? It's one of the highest developed areas. This is just to give you an idea what it's going to look like in the future at high tide. And this is the rail. So you're coming out of your rail station, stepping onto these streets, and they're all in the water. So you better be prepared. And well, this is not the only development going on. We have Kaka'ago developing. There's like one high-rise after the next. If you read the advertiser, you know what's going on down there. City and council approves one after the next one, and they're all going up here, there. I'm pretty sure Waikiki has a lot of new hotels lined up, ready for development, all these things. All in that zone where you would have a lot of problems in the future. Also, what people might be interested in is the sewer lines. I mean, increasing sea level and increasing groundwater levels would cause more brackish water in that area, which probably leads over long term to corrosion of those pipes if the water is more brackish than before. And of course, cesspools. These are the areas. I mean, I didn't know there's so many cesspools in that area. I thought it's all sewer, but there still are cesspools. What happens to a cesspool when the groundwater comes up to the surface? Do you want to know? Well, there's a lot of things to think about. And then, I mean, if this is your whole area of development, especially this area here, Kaka'ako, Alamoana, Waikiki doesn't seem to be doing too bad, except for this area here. But then all the areas behind where people live. I mean, okay, this is a golf course. Maybe we can sacrifice that back to the wetland because that's what it was before, right? Before they filled it, it was a wetland. So it's going to be a wetland again. And so we have a few things that are definitely worth considering for urban planning. And so the effect would be that there's areas that are flooded. They don't even have to be connected to the ocean. And as I said, we might get more wetlands. It's also changing the soil and the surface drainage. So we're increasing the pore pressure, we're decreasing slope stability. I don't know in the flat area if that makes too much of a difference, but for the high rises it might. I'm not quite sure. I'm not a geotechnical engineer, but there's other people that can look at that. Rising aquifer salinity could lead to corrosion of the subsurface structures. Cesspools, we talked about that. So in all the infrastructure, hospitals, wastewater treatment, roadways alone. I mean, what do you do when all the streets are flooded? You can't drive through them. No ambulance can drive through it. You can't wait till low tide until you can drive through. That's not really an option. So definitely this needs to be considered in future development plans and looked at in more detail. So this is again the pictures to show you that the freshwater-lens thickness does not really, it's not really threatened by the rise of sea level for our Rotzoll aquifer. And so we have climate change. We have to deal with it. Sea level is going to rise. We'll do sea erosion and coastal flooding. And because the groundwater levels are above mean sea level, they will rise simultaneously with sea level, cause about 50% more flooding than without factoring it in. And yeah, not much impact on the water resources, which is good. Thank God to the cap rock. And but to adapt, it's very important to monitor the groundwater levels and include the impact from sea level rise in any development plans. And if you have more interest in what's going on, Chip Fletcher has a website that explains all the nitty-gritty things about climate change and what he's been up to with this regard. So I invite you to go to his website and look at all these things. Thank you. Unless you have more questions. How did I do? 18? Did I make it?
Nothing. Nobody dies.
Questions?
Yes.
I'd like to make one quick comment about the first one.
Yeah.
When the seawater level goes up 1 foot or 3 feet,
Yeah.
it indeed will affect the water resources very badly.
In the cap rock, yes.
Even in the basalt, because when we say 1 foot and 3 feet, that's the water table. Everything go up. Based on the Gabon-Hesper relationship, the lens will shrink much more than that.
If you have more
so the
drainage,
midpoint will go up 40 times. So if it's 3 feet, seawater level rising, it will cost roughly 120 feet up, which will reduce the freshwater supply drastically. Another point is, in addition to that, when the sea level go up that much, it will induce much larger mixing phenomenon. So dispersion will go up. So
that's certainly
the
pointless.
good quality of water will be threatened. So it is not a problem, rather it's a very serious problem for water resource.
I know.
Also. Another quick point is about sewer line, because I'm wastewater engineer. The sewer, ordinarily the sewer accepts about 30% water, additional water, we call it inflow, because the groundwater will seepage into the pipeline. If the sea level go up 1 foot or 3 feet, that will induce a very serious problem of inflow, which is illustrated. It was illustrated several years ago, 2006, in Waikiki, the sewer main break. After heavy storm, the groundwater go up because the sewer subject to too much water pressure. They cannot stand, so they broke.
So they might have to replace all
So
the
every
sewer
sewer line will be affected very badly also. So in addition to what you said, there are probably more problems.
So how does the water get from the aquifer into the sewer line?
The sewer line, although it's a pipeline, but it's complete, it's not 100% sealed.
The joint.
There always some place the water can get in.
So that means
As-
also the sewer gets out.
Honey?
The sewer also gets out?
No,
The sewage?
sewer cannot get out because it's the pressure always the other way.
Okay.
So that, especially when you have a pumping, like a Waikiki is the lowland. We have several large pumping stations to increase the sewer pressure in order to send to the same island. So that place is very critical. That's what's happened in 2006. If you have a sea level rising, say 3 feet, the entire sewer system has to be renovated. That's $1 billion project, I would say. So it's a big problem. There are lots of other problems.
Oh yeah, that's not the only one, I agree.
We'll all be dead by then, right? Okay.
Garrett?
I can sort of consider myself a visitor to these seminars, and I'm certainly not an expert. Should I take away from what you said here, 1,000 feet of fresh water?
No. That's the distance between
800 feet, or 800?
No, not to the midpoint. That's the
Okay, so
50%
900
salinity.
feet
You
fresh
can't
water.
drink 50% seawater. Even, I mean, 200.
700 feet of fresh water.
No, it's even less. It's a lot less.
600.
Okay.
So that transitions out of that one. Anyway, so we have 500 feet, hundreds of feet of fresh water. It's not changing very much by pumping. So should I take away and tell all my relatives that we don't have a water problem? In other words, I mean, you're
I think we have a bigger water problem from overusing it, from overpumping, than from sea level rise.
But you said the change was very small, and we're within 75% of our sustainable levels.
And what you said about the borehole effects of the nearby pumping wells seems to indicate that our estimates may be that it's rising faster. It is not accurate, that the rise might be apparently faster.
As I said before, is that the top of the transition zone, if you're believing your estimate, you might over-predict. You still have a bigger freshwater lens because you think it's a lot thinner if the thing goes up.
Right.
So if you're thinking, oh, it's already super accurate, but it's not even, then it's good,
So
because you're still on the
we may
good
be a little
side.
premature in our worries about running out of fresh water a little bit.
Yeah. I think we still have enough freshwater, but look
Here
here.
you're talking about 0, 20%.
Let's go back to Garrett's question.
No storage.
So what do you define as sustainable? I would think any rise is not sustainable.
Well, let's turn the question to the Water Commission.
Good answer.
The Weather Commission is supposed to be deciding this on the basis of scientific investigations.
So back to you.
And I guess this is a scientific investigation that would drive those decisions, right? Is that what you're
Correct.
saying?
I mean, the main thing also is that you do see a lot of, well, the whole freshwater lens system is very slow in its response. So say if I stop pumping for 5 years, you probably won't even see a huge difference. Locally, maybe within the well, because the borehole flow goes down, but then overall, it takes a lot longer for the whole thing to reach equilibrium, right? So the effects that we're seeing now are still, people still say that, for example, in Maui, you still see a lot of effects just based on the pumping that we had 10, 20 years ago, 30 years ago. However, there's more development coming, so it's not like we're gonna reduce pumpage. Although, no, it's not right, it's not right. Wait, we're gonna take this back, because the Water Commission, every time the water supply gives a talk, they just say how much less they pump because of all the water saving units and all the things. So I think developments in general are not too bad from a water perspective, because all the new inventions that come up with the water saving toilet and all these. I mean, when Barry comes up and talks about from the water supply and comes up and talks about how much less water they used in the past 3 or 4 years on the island of Oahu, I'm stunned. It's like, wow, this is crazy how much less water they use, and that's good. I mean, that is very good. So I don't think we have a huge problem with Oahu with the water resources. And we definitely have to have an eye on it, and we have to look at all these things. But overall, the freshwater-lens aquifer is so thick that we have a really large buffer at this point. Of course, we have to keep monitoring and see what's going on.
Some area, Kolja, like that is competing with demands, like on Maui, say, there is shortages.
Well, of course, and ever there's all the developments going on. Ever wants to have water, but they don't have recharge. So clearly.
And also in the future, if we have climate change, less likely that we have less recharge, so more salt water erosion.
Don't some of the USGS monitoring wells show, in fact, an opposite trend, a freshening of the water? I'm not sure if that's true. No, none are showing that.
No, not that I'm aware of. There's a few ones that are stationary, but I haven't seen any ones that grow thicker. But maybe they're not just monitored long enough to really tell the trend. I mean, I only had 10 years of data that I looked at. Statistically, it's very short. Especially if you look at the 40, 50 years, it's been pumped very hard. Thomas.
I just had a question about the very first slide of your talk, your conceptual sketch showing the cap rock. So it's clear that the cap rock is a really important ingredient of the whole island system. I was just curious if that's vulnerable to any climate change, like the changing age of seawater or more wave action. And also, if the inundation is a problem, maybe you can just punch a hole for that.
Well, certainly the water quality is going to change in the cap rock. But as I said, nobody cares about it. There's a few wells in the cap rock that are used for cooling purposes, for irrigation of the parks, for what else?
No, what I mean is the cap rock may be vulnerable to erosion that might accelerate climate change.
Yeah, of course it's. I mean, this is technically, not going to skip word, but all the coastal erosion, that's part of the cap rock. I mean, it's all coastal sediments. You just merge it into this term of everything that's not basalt aquifer. And so all the limestone deposits, alluvial deposits, marine deposits, mud, clay, whatever you find that's not basaltic rock layers is cap rock. And they're very thick. I mean, they're about 1,000 feet thick on the coastline in Pearl Harbor. That's fairly thick.
And also marinas are bad for the environment, of course. When you cut the cover to create marinas, that's not very good. Any other questions? Okay, all right, thanks.